There have been some concerns expressed by NGOs over environmental performance. And just recently, we have some more studies, including one from the Closed Loop Partners, looking at some of the issues around both climate impacts, water impacts, and toxicity. And then we'll just close with some of the top lines out of this. So with that, I think we're ready to get going. There's a lot of confusion over what is advanced recycling. We use the terms advanced recycling, molecular recycling, and chemical recycling synonymously. And they do mean pretty much the same things, but they can be used differently. I think chemical recycling is typically associated with what we call conversion technologies, many of which have been around for many, many years. But when we use the term advanced recycling, we're really talking about a very diverse suite of technologies, some that can regenerate polymers, others break polymers down to different components, whether it's monomers or intermediates, and they can be used to create new plastics, fuels, or other hydrocarbon-based products. So I don't think that there is a definition of how we consider these technologies, but the way I think about them is really defining them by the products that they produce and the degree to which polymers are decomposed. So if you look at this graphic and go from left to right, you'll see as we go across those green circles, you have increasing degrees of decomposition with the various technologies. And those little sort of light blue boxes give you some sense of the types of technologies that are associated. So if we look at purification, for instance, we have solvent and non-solvent based purification technologies. These do not break any polymer chains. They simply purify the polymer. So it removes additives, colorants, dyes, and it creates a like virgin polymer that can then re-extrude it and go right back into production. It's a relatively new area. It had been around in the past, but there were some concerns around the toxicity of solvents. So what we've seen recently is some real innovation and improvements on these types of technologies. Then we get into decomposition, and this is where there's a really broad range of technologies. But what they particularly do is break polymers down into their monomers or chemical intermediates. And that could mean slightly longer chains. So there is a real diverse range of technologies under this category of decomposition. Some of them are chemical-based, like methanolysis and glycolysis. Others are what we more traditionally think about chemical recycling, like pyrolysis can be under here, because certain polymers under pyrolysis will yield their monomers. And then we have some microwave or very selective decomposition type of technologies as well. Then we move to conversion, and this is really where I think historically there have been concerns over conversion technologies. Most of them come out of the petrochemical industry. Pyrolysis and gasification have been around for 100 years. They're quite well understood, but their application to plastics is relatively new. Then we have some innovation in this area as well, things using hydrothermal processes, using supercritical water. These break the polymers down into their very fundamental C fractions, or what we call their hydrocarbon fractions. And that can be either in liquid form or they can create syngases, which are very elemental. But those are the foundations of creating new hydrocarbons. So what you can see on the upside of those green circles is the types of products that can go back into new plastics, and then the products that can come out either as fuels, as hydrocarbon products like waxes, or in some cases, they're just petrochemical intermediates. So let's just talk about a few things about what differentiates advanced recycling from mechanical recycling. They're quite diverse, and we see more technologies coming up all the time, including some that are enzymatic. So we have some really interesting green chemistry types of technologies. However, there is a legacy perception, particularly in the NGO community, that's very negative around chemical recycling. And that's particularly things like gasification and pyrolysis, where they liken it to incineration. However, these are not combustion or incineration processes. You are maintaining the molecules of the material, but it depends on where they go. If they go into fuel, then yes, they will be combusted. But if it goes back into the value chain for plastics, then we are in fact keeping those molecules in circulation. So today, there aren't a lot of commercial scale operations. And when I say commercial, we're talking about things on the scale of 100,000 metric tons or larger. However, you can see I was reviewing a paper by Rabobank. They think that there's going to be a huge amount of growth in this area. They're predicting up to 140 new facilities by 2025 with the capacity between 3 and 4 million metric tons a year. So that's a global statistic. The scale of these technologies relative to mechanical tends to be quite large. They're capital intensive. And as you move to that right-hand side of the chart around conversion, you either have to have an offtake partner who can take those hydrocarbon products and put them into a refinery, or you need to be part of an integrated facility. And that is actually a very interesting area to look at because there's a lot of efficiency integrated petrochemical processes. The one thing about them is that they are really focusing on hard to recycle plastics and formats. And when I say formats, that could be things like sachets and pouches, or it could be apparel, durable goods, and formats that we typically don't see either in municipal collection or going through a MRF. So they sort of open the door on possibilities for what we could recover. However, they also are typically looking for low to no cost feedstocks. Unlike mechanical, they have to be looking, the cost of feedstock they're very sensitive to. However, in some areas where there's supportive policy, they may be paid a gate fee to take these hard to recycle materials. So that really influences the business model. In almost all cases, they have to pre-process their feedstocks, which adds both capital and O&M costs to the system. Now, there are some technologies, particularly in Europe, that are buying pre-processed, but then you're paying for that. So there's a really interesting interview with the head of sustainability at the Science Med Group, and he was talking about how challenging he thinks advanced recycling technologies are going to be in Southeast Asia, principally because of the lack of supportive policy, the lack of source segregation, and the state of collection infrastructure today. And I think as we go through this presentation, we will sort of talk about those themes. We don't really know that the economics are unproven at this point. However, we do have really good insights on what influences the economics of them. And as I just suggested, the policy environment in which a technology is being placed will have a lot to do with their economics. If you're getting paid a gate fee versus having to purchase feedstock, that obviously has a big influence on your overall economics. So when you get into the middle of this chart, you'll see the feedstock transformation and output. Those are the typical generic steps for any advanced recycling technology. They're not so different than mechanical recycling, but what you see is that the reliability and quality and the cost of feedstocks to have a lot to do with the overall economics. And what we see is that this is probably one of the biggest linchpins as technologies look to move into different markets. They have to find reliable quality supply at the right price point. And then there's a question around how much pre-processing do they need? So a lot of pyrolysis operations, they will have a mini MRF in front of the operation to make sure there's no metals. They don't want PET in there. And then they will densify or sometimes pulverize the material before it goes into the reactor. So the more surface area there is, the faster the reaction time, but that depends on the type of technology. So this is where you have CapEx and OpEx considerations and scale. The scale really has a big competitive impact as well as yield. So the quality of what goes in has a lot to do with what your overall yield will be on the outside. For me, that yield question, just like a mechanical recycling, is a really important factor on the overall economics. If I have to buy a ton of material, but my yield is only 75%, then 25% of that is not giving me product. So we see yields on some as high as 98%, and then we also see some where yields are as low as 70%. And then the output side is really around what products are they intending to produce? Are they really addressing a plastic market, fuels, or alternative products? We have some companies who are actually creating new feedstocks for new materials. There's some really interesting technologies that they could even come out of plastics, but make things like a synthetic nutrient. So there are different types of products that can be made, all sorts of different types of post-processing, depending on what the process is producing. I mentioned already that if you aren't an integrated facility, you may need an off-taker. So that makes a slightly more complicated supply chain. So I thought you guys might be interested in seeing where there are existing and proposed projects in Asia. RRS has done a ton of research in this area over the last several years, and then this Rabobank report. And I think what's really clear is India and Japan really lead in terms of the most commercial advanced recycling technologies. And those that are commercial tend to be focused on PET, their glycolysis processes. This is a type of decomposition. And the other ones are pyrolysis. And then what we see is a lot of interest, but not necessarily commercial technologies in other parts of Asia. So you'll see I tried to distinguish between sort of small pilots versus commercial versus there was just simply an announcement made. On the right-hand side, that gives you a good sense of that. So even with all these announcements, we're not seeing commercial scale facilities yet in Southeast Asia. And I just wanted to give this example, like the Siam Cement Group has a pyrolysis pilot, but it's 4,000 kilotons a year. And then Environmental Solutions in Singapore has a 20,000 kiloton facility, but I don't think it's at full capacity yet. So in the world of plastics, this is very small. And we don't have scale yet. And without scale, we're not really going to truly understand what the economics are. And I want to just mention that is not comprehensive. There's a lot more projects than that. This is based on a chart in that closed loop report on transitioning to a circular economy, where there's this nice analysis that shows the scope of materials that can be addressed by advanced recycling technologies, but also where they are in terms of their commercial development. It was a really complex chart, so I tried to break it down for you a little bit to show you how we open the door, that pale gray box in the upper left. Those are the things that we have scaled, well-established mechanical recycling processes for pretty much globally, although HDPE is a little less robust in certain parts of the world. But that's really the backbone of mechanical recycling. What advanced recycling technologies are doing is opening the door to new resins and new formats. And so you can see that we have rigid polypropylene, we have polyolefin films, that's the PE and PP films. That includes things that's a face mask. So we call those nonwovens. We have technologies that can address polystyrene and expanded polystyrene, multilaminates. And we're also now seeing some really interesting things around textiles, particularly cotton and polyester, which represent a huge portion of the overall apparel industry, as well as technologies that can take mixed plastics. And when you can take mixed plastics, that really reduces the pressure on the need for really precise segregation. So on the right-hand side, it shows you the green are things where these are developing technologies with commercial examples in the marketplace. The bright blue is where the technologies appear to be feasible, and they're usually in demonstration phase. And so the products on the right are broken out that way. So the point of this is that they have the promise of opening the universe of recoverable plastics, which is really important as we think about trying to achieve a circular economy. So this is just a bit more of a riff on that, but looking at what is the relationship between mechanical and advanced recycling, and how should we really be thinking about these? Do they compete? Do they complement? My point of view is that they're complementary, that mechanical recycling is really well tuned for these rigid plastics that are typically easy to identify and collect, PETs, HDs. It could even include PP, but they need segregated streams. These are high volume, well understood by consumers and the mechanical recyclers. The cost of these feedstocks is not at a price point that advanced recycling technologies are going to be interested in. It's too high for them, which is why they're looking at these other types of materials. So I think nonwovens is a particularly important one now that we've all been wearing face masks for 2 years. But nonwovens are a giant category. I mean, anytime you go into a hospital, you'll see people completely covered in them. In a clean room, people are in them. They have a very high melt flow index. They're a very valuable polymer, but to date, we really have not had any way to recover those. So PureCycle's purification technology is opening the door to processing that category of polypropylenes. They can process black plastics and things that we typically don't think of, like carpeting and films. But these technologies do need segregated streams, just like mechanical, of either polypropylene or particular laminates that they might be looking at. If we move into decomposition, we're bringing back monomers or perhaps intermediates. The types of materials are very similar to purification, and similarly, they need to have segregated streams. So they're not going to take a mixture of plastics. You're either going to do PETs or nylons. PA6 is a nylon, or polystyrenes. PET is used in a lot of carpeting. It's used in a lot of apparel. So this is a very interesting expansion of capacity by being able to address this other grouping of polyesters that we can't easily mechanically recycle. And then we move to the far side. And this is where I think the term feedstock flexible was used in the closed report. I really like that, because this is where conversion technologies can take mixed plastics. And it can also take materials that we probably may not want to mechanically recycle because they may be contaminated with pesticides, oils, or other fuels, and durables. So that means furniture, tables, chairs, kids' toys. There's a lot of things that conversion would handle very well. And so I know a company, and they're doing a lot of gas tanks and taking stuff out of industrial sites. So the whole point of this is, as you move to the right, we're moving into realms of plastic that, when we're in the mechanical recycling world, looking at packaging or what is really consumer waste, it really is broadening our scope. Let's pivot onto why is this so important and why is it happening? These are statistics you all are probably very familiar with. The left side of this is a chart we did of Roland Geyer's data from the production, use, and fate of all plastics ever made. And I think it's really helpful to see, when you look at the thick lines under the sector consumption, you can see how big packaging is and how short the duration is. And it just kind of gives you the context about why we need to address some of these areas. But you'll see there are a lot of them, like consumer and institutional. That's a pretty short time frame too. Textiles is only 5 years. So we have a lot of short-term products out there, as well as a big pool of durables out there that we need to address. And as we look forward in time, the plastic industry is huge, and it's just getting huger faster. And this is not just a material issue, but it's a climate issue, because if we keep extracting virgin resources, new plastic, you can see the projection here by 2030, the emissions from the plastic industry would be equivalent to 295 new coal burning power plants. And our planet just simply cannot afford that. So we have these very fast moving plastics are growing really rapidly, driven largely by emerging economies. And we don't have scaled interventions yet. We have mechanical recycling, but it is not at the scale with which we produce plastic. And that's what we have to think about, especially as we look at ocean plastic issues and mismanagement issues. So some of these hard to recycle materials, so 11 million metric tons of plastics enter the ocean every year. 46% of that is what we would call hard to recycle plastics: films, wraps, sachets, bags. And so the question is, how do we get that back? And I think that's where we have to be thinking that advanced recycling maybe can provide a solution for that. I've had some interesting conversations recently where I think people did not really understand the role that the circular economy was playing in driving advanced recycling technologies. So you all are probably familiar with the Ellen MacArthur Foundation and their plastic packs, which are really their implementation platform for the new plastic economy and this circular economy vision for plastic packaging in particular. It has a really important role in harmonizing goals globally and also driving policy that's supportive of bringing materials, keeping plastics in circulation. But one of the things it has is it's driving recycled content goals. And I'm going to show you some charts in a second that just show you These content goals are very much driving advanced recycling technologies today. Their basics are we need to eliminate unnecessary and problematic packaging through redesign and innovation, move from single use to reuse. Plastic packaging should be reusable, recyclable, or compostable. And we need to increase the reuse, collection, and recycling. So this is having a huge impact globally in every market we have been looking at. The chart on the lower right is a broader context. It's focused on PE only, but the bars show you the demand for recycled materials, recycled PE in terms of million metric tons. And then the lines are the percentage of recycled as a percentage of total demand. So we really are underperforming on the recycling side to really meet what we have for demand. I mean, the best is 15%. This is why we need all tools in the toolbox to address this. And I'm showing you this because this just shows you the opportunity. The gray is the opportunity. So this is not looking at only packaging or anything. This is the overall plastic recycling rate. And if we want to address virgin production, we have to address these gray bars because otherwise they're being replaced by virgin material every year. And I think it's important to keep that big context because we can tend to look at recycling rates like PET bottles. Well, in the scope of all things, it's important, but we have all this other stuff we need to do as well. Mechanical recycling is clearly the most direct path. It's going to be the most efficient path, but it only addresses a portion of all plastic packaging and products. So a couple of things need to change to grow our solution set. And part of it is mechanical recycling has typically been a low-cost alternative to virgin. And the vast majority of plastics are downcycled into applications with less rigorous requirements in packaging. So we put it in textiles, pipe, or lumber. That model is not sufficient to build a circular economy. We need policies that are going to incentivize collection, education, infrastructure, and help us scale whatever technologies, mechanical or advanced. But we also need disincentives. We cannot have cheap or no cost disposal. And we need to disincentivize the use of virgin resources. So part of this is we have to increase the scope and scale, and we have to shift the business model. So we need to move into higher grade, higher value end markets that value PCR and willing to pay for it. The things that come to mind are like packaging, apparel, could be electronics or other things. And that is happening. I think we're starting to see that, but we need it to accelerate. So this is where I think advanced recycling technologies, perhaps this is their role. So I think that when scaled, they can complement. And in one very important way, in that they can help address that unmet portion of plastics we're not addressing today. They can fill in the gap where we have technical barriers to mechanical recycling. They can address the physical, the color, odor, and physical degradation that build up in mechanical recycled plastics. That if we want to keep them, so we recycle a bottle 7 times, at which point it starts to get pretty gray and doesn't look so great, advanced recycling can actually upgrade that material so it's just like virgin and then goes back into production without having to extract virgin resources. That I think is really important to keep in mind is that big system picture. So the chart on the left, this is from IHS Markets. They've done some scenario planning looking at what happens if business as usual. The green line is the demand for virgin plastic through 2050. And then what you see underneath it is in green is mechanical recycling displacing virgin. You have markets that are durable markets that are big demand sinks like lumber, asphalt. Chemical recycling is that little purple line. And then you can see landfill. And then there's a giant gap between that and the virgin line. That assumes we just keep going on as we are. Scenario B is there is a step change in social and political attitudes towards energy, climate, and the environment. So this is policies, prioritizing climate, and at the same time, disincentivizing the demand for virgin hydrocarbons. And you can see how long that time frame is. And that's talking about revolutionary change. But it does significantly close that gap. You'll see, landfill and energy recovery is still a big portion of this, but it does accelerate it pretty substantially. I mean, it goes from 20 to slightly over 50%. So you can see how important policy is, as well as, I think, the education of policymakers and citizens on how important this is. It's not going to solve it, but it starts to play a big role in it. I will tell you that one of the very discouraging things is how long it takes for policy you can pass, but it can take 5 years before it's implemented. So that is another issue that we have to face. So I just wanted to talk about the challenges are very similar for mechanical and advanced recycling. I kind of lumped them by general challenges. You need source segregated feedstock. Collection of plastics today sort of globally is not scaled to our use, to the scale of use. We typically collect only limited forms. We have a real challenge with consumers. It's just all plastic. They don't really differentiate. They might differentiate between a bag and a bottle, but they're not differentiating between PET and polyethylene. Then this is the question that was brought up around sachets, the economics of collecting films and flexibles because they are so light. They're incredibly resource efficient in terms of delivering goods, but on the back end, they are really challenging. So this is where I think policy is going to play a really important role. Some additional challenges for advanced recycling is the scale, the volume that they're looking for. And you can't turn these facilities off. They need to have that material coming in the door all the time. And they're also targeting polymers that are not collected in today's typical systems. So there's got to be some growth in that area. So I think that is important for context, but I did want to just touch on the environmental performance issues because this is an area that it's a real sticking point where the entire class of advanced recycling technologies is getting judged by legacy performance of pyrolysis from 35 years ago. I think the technologies I've reviewed, they have done a lot of work on improving their environmental performance. They're really thinking about it. They have to comply with all air regulations. But like any industrial process, if it's not well run, it's not going to perform well. So it's not just the technology, but it's the operator is really, really critical in this. The recent LCAs have come out showing that they have a greenhouse gas benefit. It's not insubstantial. It's 40%, 39% in a market like the US, where we typically landfill plastics, so there's no carbon impact. However, when you move to a market that incinerates plastic, the benefit of these technologies is really realized because if we're burning plastic, we're putting all that carbon up into the atmosphere. So we do see environmental benefit. And I think that the volume of information around these technologies is really growing. So the key takeaways are the plastic industry is growing dramatically over the next few decades, and we have to address and reduce the use of virgin plastics. Not all advanced recycling technologies are the same. We really need to look at them independently, evaluate them, and regulate them independently. These technologies have that potential to grow the universe of recovered plastics and upgrade not only hard to recycle plastics, but degraded mechanically recycled plastics. So we can keep a big pool in circulation. There is growing evidence that there is both carbon and environmental benefits to these technologies. They're not the same for all, but they're there. It's still a very nascent industry. We have a lot of questions still about how things are going to roll out, but we expect a lot of growth over the next decade. The biggest challenges to that growth are finding the supply, reliable volumes of quality feedstock, and demonstrating the business model. And that's where policy really plays a role. Policy can be supportive or it can be a real challenge. And I think this is local infrastructure. I'm really talking about collection and policy. They're going to play a big role on how fast the adoption and effectiveness of these technologies roll out.